Okay, here is the November 2014 question on the photoelectric effect. It says to you, ultraviolet light is incident on a photocell with a potassium cathode as shown below. The threshold frequency of potassium is 5,548 times 10 to the 14 Hertz. Define the term threshold frequency. So here it is up top here. It's the minimum frequency of a photon of light needed to emit electrons from the surface of a metal. It's usually a metal, but they put sometimes substance in the answer. Now it says to you the maximum speed of the ejected photoelectron is 5,33 times 10 to the 5 meters per second. Calculate the wavelength of the ultraviolet light used. Okay, so you can see this is 5 marks. It's not going to be in and out in a hurry. Okay, so let's think about what's happening here. We are shining light on here, and the light is causing little photoelectrons to be emitted, and they are being emitted with this speed. So we know from this formula over here, okay, the energy that you put onto the cathode is going to be split up into some energy, the work function, which is what is needed to emit the electron, plus the kinetic energy that the electron jumps out with, okay. So the energy is going to be Planck's constant times the threshold frequency plus a half mv squared, which is this V max, because this is the emitted photoelectrons. So we know what has got the kinetic energy. The electrons have got the kinetic energy. So this m in this formula is going to be the mass of the electron, okay. So when we calculate the wavelength of the ultraviolet light used, we are wanting to know the ultraviolet light that is giving us this energy value, okay? And we have to then be using one of the other waves, light and sound formulas to calculate wavelength. But for now, let's concentrate on what we know. We can find out exactly how much energy we were inputting here because we know Planck's constant on the data sheet. 6,63 times 10 to the negative 34. We know the threshold frequency because it's given in the question. So this is 5,548 times 10 to the 14. And then we know a half times 9,11 times 10 to the negative 31. A half m. And now I've got to find some way to write this in here. So I'm going to go down below, but remember we're multiplying here. A half of the maximum speed was 5,33 times 10 to the 5. And if you look, that's meters per second, so it's the correct unit. Now remember this formula says kinetic energy is a half mv squared, so a half times the mass of an electron times the velocity squared. So you need to plug this all into your calculator. The threshold frequency plus the energy that the electrons are jumping out at, and you end up with some value that looks like this, okay. So here is the energy, and this is the total energy that has been put in, which is then being split up into part of it to eject the electron and part of it to give the electron a escape velocity thingy there, okay. But it didn't ask me how much is this energy. It asked me what is the wavelength of the light that is used to create this. So remember the wavelength is lambda. So I need to get a formula that's got lambda and also energy. So we know that E equals HF, but we also know from the waves light and sound E equals HC over lambda. So we can say 4,972 times 10 to the negative 19, that's the total energy that we input, is equal to Planck's constant, which is the H, 6,63 times 10 to the negative 34. And this is electromagnetic radiation, so this is 3 times 10 to the 8 over lambda. So by the power invested in you with algebra, you will get a value of lambda is 4,00 times 10 to the negative 7, and my unit for lambda, wavelength, the distance between 2 points in phase, it's a distance, we measure it in meters. So my wavelength is going to be 4 times 10 to the negative 7 meters. Now it says to you, the photocell is now replaced by another photocell with a rubidium cathode. The maximum speed of the ejected photoelectron is 6,1 times 10 to the 5 meters per second when the same ultraviolet light source is used. So what's happened here? Here's my one escape velocity. Look over here. Okay, 5,33 times 10 to the 5. And my other, I don't know if it can possibly be called escape velocity, but that's kind of in my brain. I think of it as the velocity that the little electrons escape the metal with. So now this one's maximum speed, the rubidium's maximum speed, is greater than the potassium's maximum speed. So if you look at that formula, the energy that you put in is equal to W0 plus EK. But now the EK has gone up, okay? The E has stayed the same because we didn't change the light. So if this has gone up and they must remain equal, the work function must have decreased. So the answer to 10.3 is smaller than, because for the equation to be equal, the amount of energy you put in stayed the same, but the kinetic energy increased, so that means the work function must be smaller than. Okay, so now it says explain the answer. So you say the same light source, yeah, has the same energy or frequency or wavelength, okay, and so that is not changed, okay, but the photoelectron, you must say for which photoelectron, but the photoelectron from rubidium, okay, from rubidium is faster than from potassium, so the work function of rubidium must be less than that of potassium. There we go, and we are done with this question.